Hey everyone, welcome back to the Deep Dive. We all want to learn new things, right? But who's got time for information overload? Not us,
Yeah.
and definitely not you.
That's why we're here, to get to the good stuff quickly. And today we're going to be talking about learning itself. Sounds kind of meta, right? But stick with me because we're going to be exploring some really fascinating research on how we acquire new skills.
So basically, how to become awesome at learning new things. I'm in. You know I'm always up for that.
Absolutely. We're diving into educational psychology today, and specifically, we'll be looking at a paper with a bit of a dense title, Accounting for Beneficial Effects of Worked Examples in Tutored Problem Solving.
Yeah, you sent that one over, and I have to admit, the title itself didn't exactly grab me at first. But once I dug into it,
Yeah.
wow, this is some really cool stuff about how we can make learning way more efficient and effective.
It totally is. And the key here is this idea of worked examples. Basically, it means seeing a problem completely worked out step by step, like a super detailed instruction manual for your brain.
Oh, okay.
Yeah.
That makes a lot more sense. Like instead of just being thrown a problem and told to sink or swim, you get to see exactly how an expert would tackle it.
Exactly. And this research looks at how worked examples can supercharge learning, especially when they're used in these computer-based tutoring systems called cognitive tutors.
We've touched on those before on the show, but just as a refresher, what makes these cognitive tutors different from like a simple online quiz?
Right. So with those quizzes, you're kind of on your own.
Hmm.
But cognitive tutors, they're much more sophisticated. They can actually adapt to how you're learning.
So it's like having a personalized tutor built right into the software.
You got it. And the big question this research tackles is, when and why is it actually smarter to study worked examples? When is that a more efficient way to learn than just jumping in and trying to solve problems from scratch?
Yeah, that's the million-dollar question, right? Because we've all been in those situations where we're just banging our head against the wall trying to figure something out. Maybe there's a better way.
That's what we're going to find out. So the paper starts off by looking at what we already knew about work examples from previous research. And one of the big takeaways, they're super helpful when you're first starting out with something new, like in the early stages of learning a skill.
Okay, that makes intuitive sense. You got to see how it's done before you can really do it yourself, right?
Yeah, totally. Like if you're trying to learn to play guitar, watching someone else play the chords first is going to be way more helpful than just strumming randomly and hoping for the best.
Right. You need that model to follow. But I'm guessing it's not as simple as just watching examples forever.
Nope, there's a bit more to it. Research also shows that as you get more skilled, actually solving problems yourself becomes more and more important. You can't just passively absorb information forever. You got to put it into practice.
So it's about finding that balance, right?
Right.
Early on, you need more examples, and then as you progress, you shift towards more active problem solving.
Exactly. It's not a one-size-fits-all approach. It really depends on where you are in the learning journey. And another interesting thing they found was that mixing examples and problems together is generally better than doing them in separate blocks. Like, see an example, try a problem, see another example, try another problem, and so on.
Ah, so it's like interleaving. We've talked about that before on the show.
Yeah.
That back and forth seems to help solidify the learning.
Yeah, exactly. It keeps your brain engaged and prevents you from getting stuck in one mode for too long. And taking that idea a step further, researchers have found that fading the examples as you learn is even more effective.
Fading. Okay, now we're getting a little technical. Break that down for me.
So fading just means you gradually reduce the amount of detail you're giving in the worked examples. You start with a really thorough walkthrough, and then you slowly remove some of the steps, forcing the learner to fill in the gaps more and more on their own.
Oh, I see. So it's like taking off the training wheels gradually.
Yeah, perfect analogy. You're slowly building up the learner's independence. And they also found that worked examples are most effective when they break down the problem into those smaller subgoals. So it's not just about seeing the steps, it's about understanding why each step is taken and how it contributes to the overall solution.
Makes sense. It's like you're giving the learner a roadmap, but they still have to do the driving. And it reminds me of those cooking shows where they break down a complex recipe into those manageable steps. It just makes the whole process less daunting.
Absolutely. And finally, one of the most important things they discovered was that explaining the steps in an example to yourself out loud or even in your head can really make a huge difference in how much you learn.
That's so interesting, just the act of talking yourself through it. solidifies the understanding.
Yeah, that's right. It forces you to actively engage with the material and connect it to what you already know. Now, all of this research on worked examples was a great starting point, but the authors of this paper noticed a pretty significant limitation in most of those earlier studies.
Okay, so what was missing from the picture?
Well, most of the previous research compared worked examples to solving problems without any real-time help or feedback. I was like, here's an example. Now try these problems completely on your own. Good luck.
Ah, so it was a pretty stark contrast. No safety net for the problem-solving group.
Right, exactly. And that's where these cognitive tutors come in. They change the game completely.
Remind us again how they work.
Well, they're not just about giving you a bunch of problems and seeing if you get them right or wrong. They're actually designed to adapt to how you're learning. They can choose problems that are appropriate for your skill level, they can track different ways you might try to solve a problem, and they give you feedback every step of the way. Plus, they can offer hints and even show you worked examples that are specifically relevant to the difficulty you're having.
It's like having a super attentive tutor who's right there with you, guiding you through the process.
Yeah, that's a great way to think about it. And research has shown time and time again that these cognitive tutors are way more effective for learning than just struggling through problems on your own.
What are some of the features that make them so powerful?
Well, they have this thing called model tracing, which basically means they can understand and adapt to the different approaches a student might take to solve a problem. It's like the tutor has a mental model of all the correct ways to get to the solution. Then there's knowledge tracing, which is how they keep track of what you understand and use that to pick the right challenge for you.
So it's like they're constantly assessing where you're at and adjusting the learning path accordingly.
Yep, exactly. And a lot of them will also prompt you to explain your reasoning, which, as we've already discussed, is a huge boost for learning.
So it's like they're incorporating all of these evidence-based techniques to make learning as efficient and effective as possible. And it's not just some theoretical idea, right? These cognitive tutors are actually being used out there in the real world.
Oh, yeah, big time. In fact, they're used in tons of schools across the U.S., and there have been loads of studies done in real classrooms showing that students who use cognitive tutor courses do way better in math compared to those who are taught with traditional methods.
Wow, that's impressive. It's not just some lab experiment. It's actually making a difference in real students' lives.
So, bringing it back to worked examples, the researchers are basically saying that studying their impact within a cognitive tutor environment is an even tougher test.
Right, because the tutor is already providing so much support, the bar is set higher. If worked examples still show benefits on top of that, it really means something.
It's like saying, okay, we've already given you this awesome coach and training program. Now let's see if adding this one extra element, these work examples, can push you even further.
Exactly. And another cool thing about cognitive tutors is that they're designed to minimize what's called extraneous cognitive load.
Yeah.
Basically, that's all the mental effort that's not directly related to learning the actual skill. So it's like mental clutter, stuff that distracts you from the real learning.
Yeah, exactly. Think about trying to learn something from a super confusing textbook. You're spending so much energy just trying to figure out what they're even saying that you have less brain power left to actually absorb the information.
I've definitely been there. It's exhausting. So how do these cognitive tutors help with that?
Well, as we mentioned, they provide clear sub-goals, they give you immediate feedback so you don't waste time going down the wrong path, and they offer those bottom-out hints, which basically give you the answer for a step if you're totally stuck. It's all about removing those unnecessary obstacles so you can focus on the core learning.
It's like they're creating this clean, streamlined learning environment for your brain. I like it. And the paper goes into detail about a specific geometry cognitive tutor used in some of their research. Can you describe that one for us?
Sure, so this particular tutor had a few key components. First, there was an interactive diagram that students could use to visualize the problem. Then they had a table that listed all the solution steps in order so they could see the roadmap right from the start. And of course, it gave feedback after each step. If they got stuck, they could ask for hints. And one of the most important features was that it prompted students to explain the geometric theorem that justified each step.
Ah, so that self-explanation element is built right in. They're really hitting all the key points for effective learning here. And, you mentioned that the tutor shows the sub-goals in that table. Does that mean the students don't have to think about what the next step is at all?
Well, not quite. The table tells them what the next goal is, but they still have to figure out how to get there. The researchers make this distinction between problem search, which is figuring out the next subgoal, and knowledge search, which is figuring out how to actually achieve that goal.
So the tutor helps you with the what, but you still have to use your brain power for the how.
Exactly. It's like having a GPS that tells you where to go, but doesn't tell you exactly how to drive there. You still have to navigate the roads and make decisions along the way.
I like that analogy.
Yeah.
It's guidance, not hand-holding. And the paper also mentions that the problems in some of the studies were structured in a specific way, starting with easier problems and gradually getting more challenging. How did that work?
So, in the geometry studies, for example, they started with simpler one-step problems that focused on single geometry rules. Then they gradually increased the complexity, introducing multi-step problems that required combining different rules. This gradual increase in difficulty is called intrinsic load, which basically refers to the inherent difficulty of the problem itself.
So it's like they're slowly building up the challenge, making
Yeah.
sure the learners have a solid foundation before throwing them into the deep end.
Exactly. And now we get to the heart of the matter. What did they find when they added worked examples to these already super supportive cognitive tutors?
Yeah, this is what we've been building up to. What happened? Did the examples make a noticeable difference?
They did. And the main question they were trying to answer was whether adding worked examples would either speed up learning or lead to better learning outcomes, like improved retention or transfer.
So basically, can we learn the same amount in less time, or can we learn even more in the same amount of time?
Right. And how did they actually incorporate those examples into the tutors?
Well, they tried a few different approaches. In the geometry studies, they provided some of the numerical answer steps, along with a brief explanation of the math involved. Then the students had to explain the geometric reasoning behind that step.
So it's like they were getting a little bit of a nudge in the right direction, but they still had to do the heavy lifting of understanding the concepts.
Yeah, exactly. And they also used this technique called fading, where they gradually reduced the number of worked out steps as the students progressed.
So less hand-holding over time, encouraging more independence. And what about in the other subjects, like chemistry and algebra? In those subjects, they often used example problem pairs. So the students would study a worked example, sometimes with a video of an expert explaining it, and then they'd try a similar problem on their own.
So different ways of weaving in the examples depending on the subject. Okay, drum roll, please. What were the results?
Well, across those 8 studies, they found some really interesting patterns. One of the most consistent findings was that the example-enriched tutors often led to the same level of learning as the regular tutors, but in significantly less time.
Wow, so students were able to learn just as much, but they got there faster. That's huge. Talk about efficiency.
It is, and some studies showed that students who learned with the example-enriched tutors actually had better retention of the material over time.
So not only did they learn faster, they also remembered it better. That's a win-win.
It is, and one of the geometry studies even found that students who used examples were better at transferring what they had learned to new types of problems.
So they weren't just memorizing steps, they were actually understanding the concepts at a deeper level that allowed them to apply that knowledge in different contexts.
Precisely, and here's the other really cool thing. In none of the studies did adding worked examples actually slow down learning or make it less effective.
So at worst, it was neutral, and at best, it was a significant improvement. That's a pretty compelling argument for using them.
Yeah, it is, but here's the catch. The benefits they saw in these studies with cognitive tutors weren't quite as big as the benefits you typically see when you compare worked examples to just giving someone a problem with absolutely no help.
That's interesting. Why do you think that is?
Well, it probably has to do with the fact that cognitive tutors are already so effective on their own. They're providing so much support and guidance that the added boost from worked examples might not be as dramatic.
It's like they're already playing in the major leagues, so the improvement from adding one more star player might not be as noticeable.
Yeah, that's a great way to put it, but it's still an improvement, which is pretty impressive. And to understand all of this, the researchers bring in cognitive load theory, or CLT. Have you heard of that?
I have, but I'm always up for a refresher. How does CLT explain why worked examples are so helpful?
So the basic idea behind CLT is that our working memory, which is where we process information, has a limited capacity. And when we're trying to learn something new, especially if it's complex, we can easily overload that working memory.
It's like trying to juggle too many balls at once. Eventually, you're going to drop something.
Exactly. And this overload can happen from what's called extraneous cognitive load, which is basically mental effort that's not directly related to the skill you're trying to learn.
So it's like mental clutter. things that distract you from the main task.
Yeah, exactly. And one of the main ways worked examples help is by reducing this extraneous load. When you're struggling to solve a problem on your own, you're using up a lot of working memory capacity just trying to figure out what to do next. But when you see a worked example, you're shown the solution path, so you don't have to waste mental energy searching for it.
So it's like you're being given the cheat code.
Kind of. And that frees up your working memory to focus on understanding the underlying concepts and building those schemas, those mental models of how to solve problems.
Makes sense. So in a way, worked examples are like cognitive shortcuts.
Yeah, that's a good way to think about it. But the researchers point out that this traditional CLT explanation might not fully apply in the context of cognitive tutors.
Okay, why is that? I thought we just established that worked examples reduce extraneous load, which is a good thing.
Right, but remember, cognitive tutors are already designed to reduce extraneous load. They're providing those sub-goals, that feedback, those hints. So the idea that worked examples are mainly beneficial for eliminating the need to keep track of sub-goals doesn't quite fit when you're already getting that support from the tutor.
Ah, got it. So it's like the tutor's already doing a lot of the heavy lifting in terms of reducing that mental clutter. So what other explanations do they offer for why worked examples might still be helpful in these tutor environments?
Well, they talk about this idea of self-generation. Basically, when you're working on a problem and you figure out the next step on your own without being given the answer, that can be really powerful for learning.
That aha moment when you solve something yourself, it definitely feels more satisfying. It seems like it sticks with you better.
Yeah, exactly. And cognitive tutors are actually designed to maximize those opportunities for self-generation, but they also look at what happens when students have to rely on those bottom-out hints, when they're completely stuck and the tutor basically gives them the answer.
Right. So in that situation, they're essentially getting the same information as someone who's studying a worked example.
Yep. But the researchers suggest that the process of getting to that point, the struggle and maybe even the frustration, might make a difference in how much they learn from that answer.
So even though they're ultimately seeing the same correct step, the path they took to get there might impact how deeply they process it.
Yeah, exactly. It's like the difference between being told how to get somewhere and actually finding your way there yourself. You might remember the route better if you had to put in the effort to figure it out.
That's a good point. So what are their specific explanations for why worked examples might still be beneficial in these tutor environments, even when they're not dramatically reducing extraneous load?
Well, one explanation is simply time savings. Worked examples give you the answer faster, so you can move through the material more quickly and potentially build those schemas faster. The time you spend struggling in a regular tutor might not always translate into better learning.
So it's about learning efficiently, making the most of your time. What's the other explanation?
The other idea is what they call effort spillover. The effort you put into trying to solve a problem, even with the support of a tutor, might actually have a negative impact on how much you learn from that bottom-out hint, which, again, is basically the same as seeing a worked example step.
Oh, that's interesting. So it's like you're so mentally drained from the struggle that you don't fully absorb the solution when it's finally given to you.
Yeah, it could be mental fatigue, or it could be a shift in focus. Like once you finally get the answer, you might just be relieved and move on without really thinking deeply about why it's the right answer.
I could definitely see that happening. And they also talk about performance orientation. What is that, and how does it play into this?
Performance orientation is basically when you're more focused on just getting the right answer than on actually understanding the material.
Like when you're just trying to get through the test without really caring about the learning.
Yeah, exactly. And they suggest that too much problem-solving practice without the support of worked examples might actually encourage this performance orientation. Students might start focusing on just getting the answer, maybe by using shortcuts or memorizing solutions, instead of really engaging with the underlying concepts.
So it's like they're gaming the system instead of really learning.
Right. And worked examples, by showing the solution path clearly, might help shift that focus back towards understanding.
Interesting. So it's not just about getting the answer, it's about understanding how you got there. Now, you mentioned earlier that some of the studies use adaptive fading of examples. How does that differ from the regular fading, and what do they find?
So with regular fading, the reduction in worked out steps follows a set schedule. Everyone gets the same level of support at the same points, regardless of how well they're actually doing. But with adaptive fading, the software adjusts based on how well each individual student is understanding the material.
So it's like personalized fading.
Yeah, exactly. The software is constantly monitoring how you're doing, and adjusting the amount of support accordingly. And what they found was that this adaptive fading actually led to better long-term retention compared to both regular fading and standard problem solving.
That makes a lot of sense. It's like the software is acting as a super attentive tutor, giving you exactly the right amount of guidance at the right time.
Exactly. And the researchers connect this to the future of cognitive load theory, which is increasingly focusing on this idea of adaptive e-learning.
So learning environments that are tailored to the individual learner, that seems like the holy grail of education, right?
It does. And they suggest that future research should look into whether this kind of adaptivity, like adaptive fading of examples, can help students develop more flexible problem-solving skills and be better prepared for future learning.
So not just learning the specific material, but learning how to learn more effectively in general. Well, this has been a fascinating deep dive. I feel like I've learned so much about how my own brain works. What are some of the key takeaways our listeners should remember?
I think the big one is that while solving problems is essential for learning, studying worked examples can be a really valuable addition to your learning toolkit, especially when you're using a supportive system like a cognitive tutor.
So it's not about choosing one or the other. It's about using both strategically to maximize your learning.
Exactly. And the research shows that worked examples can often save you time and can potentially lead to better understanding and the ability to apply what you've learned in new situations.
That's a pretty compelling argument. So as you're tackling new challenges and trying to master new skills, think about how you can incorporate worked examples into your learning process. Don't be afraid to look at how others have successfully solved similar problems. It might just be the secret ingredient to boost your learning and achieve your goals more efficiently.
And if you're interested in going even deeper, definitely check out the research on cognitive load theory and the design of effective learning environments. It's fascinating stuff, and it can really help you become a more intentional and effective learner.
Awesome. Well, thank you so much for joining us on this deep dive. We hope you found it valuable. And until next time, happy learning.
Happy learning!